Okay, so today we're going into section 3 of chapter 4, which is an interesting one. It's called L'Hopital's rule, as you see there. It's French name at the bottom. What's great about this in my mind is it's a very simple mathematical procedure. The question, the difficulty, I guess, comes in is knowing when it applies, when do you have to do it, and how to clean it up and how to answer the question. So we're going to do a little review about limits because it's what L'Hopital's rule is all about. And then we're going to understand the process, the formula, the procedure, and then the whole idea is to make it fit in with what you've already been learning the last couple sections about how to graph an equation, what it means to graph, and how the functions are going to look. So you have to remember how your limits work. So remember, when you're dealing with limits, you're looking for where is your graph going. As they tell you an x is approaching a certain number, what is the y approaching? That's the question they're asking. So in this first example, they're saying as x approaches 0. So you see from the graphic, as your two arrows, as you come from the right, and it gets closer to 0 as you come from the left, as you get closer to 0. What's happening with the y value? Well, the y value is approaching 0. That's your limit right there. Okay? Now, as x approaches infinity, this is the one that we're going to talk about. You've had this a little bit before, but we're going to talk about these different pieces. As your x is going toward the right, as x is getting bigger and bigger, going toward infinity, the question is what's happening with the y? Well, you can see your y is also going up and up. That's why the limit as x, or the limit of x as x approaches 0 is going to be also infinity. And then, of course, as you're going to the left towards negative infinity, your y value is dropping down, so that limit is negative infinity. So this is the basic y equals x function. Now we get to something that's a little more, we'll get to the more curvy types. So here's your parabola that you know. As x approaches 0, just remember, you have to check your graph from the right side and from the left side. As x approaches it from both directions, what's happening with the y's? So if I kind of look at these points, x is getting closer and closer to 0. My y is also approaching 0. Same thing from this side. X is going down, or is getting closer to 0, and the y values are getting closer to also 0. And as long as it's from both directions, from both sides, as long as you're approaching the same number, you're converging at the same place, then the limit exists and it equals 0 in this case. Now as we go toward infinity, this is our next piece. As x goes to infinity, remember they're just asking, as you go out here, what's happening to the y? Well, as you travel along this graph going more toward the right, what's happening to your y? It's coming up here to positive infinity. That's why that's your limit. And at the same time, as you go toward negative infinity, as you go this direction, what's happening to my y values? They're also going up again to positive infinity. So both limits are positive infinity. So the idea is that we're going to get a little review of how these graphs look. Just by eyeballing them, we can tell the limits. We can look at them and try to figure out what the limit is doing as you're approaching a certain number. But eventually the goal is we want to use this information to actually come up with the graph. Just by looking at the equation, we're going to learn what happens. Okay? So, a couple of things. We have 1 over x, or the x to the negative 1. That pictures what's on the right, so you can graph that if you need be, but kind of see what happens. As you're approaching 0 from the right, so remember, as x approaches 0, as you're coming in from the right side, follow your graph and you see what's going on is you're going up to positive infinity. But as you approach 0 from the left side, what happens to your y value? You're approaching negative infinity. This is a case where we're approaching 0, but from two different directions. It gives us two different limits. They're not converging to the same place. They're going completely different directions. So this officially means your limit does not exist. Okay, the limit as x approaches 0. If these have to be the same, this one and this one, they have to be the same. If not, then you get this does not exist. That's what that DNE is, in case you're not sure. So that's the goal here. And all these is just remember, check it from both directions. See if they're coming to the same spot, even if it's infinities. A lot of people, some books will even say, well, if the limit's infinity, it doesn't exist. Well, we're going to go a step further than that now. No more does not exist. The limit can be infinity or negative infinity, but if they're going different infinities, just treat them like different numbers, then you say it does not exist. But if these are both going to positive infinity, then your limit of this one would be positive infinity. Okay, so now we look at as you approach infinity. So remember, we're infinities. These are always x values. So from going out toward the right towards infinity, look at what the behavior is of the graph. So as we go out toward infinity, right here, way out here, follow the graph and ask yourself, what's happening with the y value? Well, my y values are getting smaller and smaller and smaller. They are approaching 0. As you go to the left or toward negative infinity, again, as you go out here toward negative infinity, follow the graph and ask yourself, what's happening with the y's? This one's the same thing. They're very tiny numbers. They're negative numbers, but they're getting closer and closer to 0 also. Okay, so that's your answer for both of those two pieces. All right, so now we look at a different graph, and you see y equals x to the negative 2, or essentially 1 over x squared. And we're going to ask the same questions. Okay, as you approach 0 from the right side, from here, my y looks like it's going up to positive infinity. It's getting higher and higher as I approach 0 from the right. As we approach 0 from the left, it's also going way up toward infinity. That's why the limit as x approaches 0, just plain x equals 0, is going to infinity. Okay, so you see the difference. If they're going to the same infinity, then you can say that that's your answer. If they're going to different infinities, like this one, then the answer, the limit does not exist. Last two, approaching positive infinity. Again, it's out here is positive infinity. It looks like we're approaching 0, and same thing going to negative infinity, you're getting another 0. So that's some of those right here. And you see here, they want you to use these patterns and try to figure things out. So kind of get the idea of what's going on here. As you approach 2, so look what happens. The first step in every kind of problem is plug in the x for whatever number they give you. In this case, they tell you x approaches 2, go plug in 2 and see what happens. Well, if you get a 1 over 0, because this is essentially what it becomes a 1 over 0 to the 6, which is 1 over 0. Just remember, anytime you have a small number on the bottom, the smaller your denominator gets, the bigger the fraction gets. Well, as you get a 0, it doesn't exist, but you can say it's going toward one of the infinities. It's either positive or negative infinity. We're not sure which one, so here's how you can tell. All right? Go look at numbers, and this is the first way that you did a limit, if you recall. We can't plug in 2, okay? That doesn't exist. But we can plug in numbers from the left, like 1.9, 1.99, 1.999, just to get a pattern of what's happening. Now, you can plug this into your calculator. What we're really looking at is, because I already told you, when you get a 0 on the bottom, it's going to be one of these infinities. How do you tell which one? Go plug in this one, for example, and you see what you get. You get 1.9 minus 2 to the 6th power. Well, all I'm looking for is what's the sign of that? It's a negative 0.1 to the 6th, and that's going to be a really small number on the bottom, but all I care about is what's the sign. When I have a negative right here to the 6th power, it's going to be a positive. That tells me this thing is going to positive infinity. Okay, that's all you have to do when you're playing the sign game that I call it. Okay, so from the left side, it's definitely going to positive infinity. And this is the part that's not seen right here, but if you take the limit of this as x approaches 2 from the left side of this function, it's going to positive infinity. Now we want to see what happens as you're going from the right side. So what's the limit as you approach 2 from the right side? So same thing, if I was to make a table here, I know I can't plug in 2, but I can plug in numbers just above 2. 2.1, 2.01, 2.001, etc. And all you're checking on is what's the sign going to be, because I already know it's going to be a negative. I already know it's going to be an infinity, not negative, infinity. So we're just trying to assign a value to it. So we get 1 over 0.1 to the 6th. And all I know is this is going to be a positive, that's going to be a positive. This thing also is going to positive infinity. So from the left and from the right, we know we're going to the same place. That's why this problem has a limit of infinity. Okay? So this is kind of the breakdown of how they got it here. And you'll see here on the slides, I'll kind of erase this so you can get a cleaner version. But that's your process here. So here we'll do something kind of similar. When you go to a -3 right here, so when you plug in the number and it's an even power, like I said, let's start on both of these. When you plug in the number, you get zeros on both denominators. That tells you it's going to be one of the infinities. How do you know which one it is? Well, it depends which direction you're coming from. If it's an even power, it doesn't matter the direction. It's always going to be this. Okay? It's going to be the same for left and right. When you plug in -3 from the left, just remember, from the left side, we're looking at numbers like -3.1, -3.01. That tells you you're going to get a negative in here, and then when it's an odd power, you're going to get a negative. So things you have to look for, you just have to plug in a couple of numbers just to get an idea. Here now, a little different. When you plug in infinity, remember, infinity are very big numbers. So when I'm making my table on this one, what numbers do I plug in? Well, let's try 100. Let's try 1,000. Let's try 10,000. And see what you get. You don't even have to plug these in very much. The 100 should tell you what's going to happen. When I plug in 100 in there, I get 98 to the 6th. Okay, here's what I know. That's a really big number on the bottom. When you get a big number on the bottom of a fraction, that means your entire fraction is going to be small. That's where you're getting the 0. So, couple things. When you get a 0 on the bottom, any number over 0, you're going to get either an infinity or a negative infinity, one of the two. When you get a big number, whether it's positive or negative infinity, either way, these are going to 0. All right, so those are your things you have to look for. It's just basically inverses of each other. That's what's happening when you have all of these problems. And the idea is, without even plugging in numbers, you just have to kind of recognize what the pattern is. So you see here, we get -2x to the 5th. If you're going to a negative infinity, well, look at this. First off, if you put a really big number in here, you bring it to the 5th, you still get an even bigger number. You multiply by 2, it's even a bigger number. So it's going to be an infinity of some kind, so you just have to play the sign game. It's a negative number. So a negative number to an odd power is a negative number, times a negative number right here. That's why it's a positive infinity. If you're not sure, go plug in -100, -1,000, -10,000 into that function, and you will see the pattern of what's happening. Okay, so now we look at something like y equals e to the x, our favorite natural function. The limit as x approaches 0, again, just plug that in. Anything to the 0 power, even e, the answer is 1, and it kind of matches. You look at 0, 1, it's an actual point. That's your limit. Now we look as we go to negative infinity. So literally I'm looking at this picture. As I plug in numbers further and further toward the left, it's dropping down. My y value is approaching 0. It never hits it, but that's the goal with limits, is what is it approaching? Then as I go to positive infinity, you see like a parabola. This graph is just going up forever. We're getting a positive infinity. Okay, so these are the three limits where we're talking about e to the x. Again, just plug in the number and see what you get. Even if you plug in this, the middle one, and I know it's kind of weird to plug in infinities, but let's say we plug in e to the negative infinity. I want you to remember, that means e to the positive infinity on the bottom, which means 1 over infinity, which we just talked about, is going to be a 0. On this one, when you plug in e to the infinity, well, anything to the infinity except for 0 and 1, but if you get a number to infinity, it's infinity. Okay, and these are the kind of things that you're going to do. It's not going to be a lot of intensive math. You're going to plug in some numbers sometimes, but a lot of it is just sort of trying to extrapolate what you have and where you're going with these. Okay, so show you some more of these examples. Now we get y equals e to the negative x. Notice it's the same picture, but it's a negative power, but it just flips it over. So approaching 0, you still approach a y value of 1. As x approaches negative infinity, so as it goes to the left, we're shooting upward, so it's a plus infinity. And as we're going to the right towards positive infinity, you get a 0. And you see kind of some patterns here. Okay, and this will work for just about any number, even if that's not an e. If that's 2 to the x or 5 to the x, you're going to get a similar idea. Now you get a natural log function. Okay, if you didn't know how natural log functions looks, this is what it is. Remember, inside of a log, you can only have positive numbers. That's why you don't see anything on the y-axis. You don't see anything to the left. So as you plug in a really big number here, it doesn't shoot up exponentially, but it still continues to go upward. So log of infinity is going to be still infinity, all right, when we get to that one. Now let's look at 0. Notice you can't take the limit of 0 normally without the plus minus because that implies checking from the left and the right. There is no left behavior to check. So the only thing you can do with 0 is check it from coming from the right side. So as we approach 0, what's happening to our y value? It's dropping down and down. There's our negative infinity. And I'll say it again. Limits are always asking about y values. What is the behavior? What's happening with y as x does this? Now as we go out to the right, x is to infinity. We get the natural log of infinity. And remember, any log of infinity is just plain infinity. Okay, so a couple things. Some little shortcuts you can see here. When I plug in infinity as an exponent, I'll kind of walk you through how I approach these. If you take 4 times infinity, guess what? You still have infinity. If you get a number to the infinity power, you still get infinity. If you get 3 times infinity, you still get infinity. That's all this is, just a super big infinity. Here, a little different. When you plug in infinity, I get a negative infinity up here. Negative 2 times infinity is negative infinity. So think of that as an e to the infinity on the bottom. You don't have to always write these out, but it doesn't hurt. So we have that. That's an infinity. That's basically e to the negative infinity, which means 5 over e to the infinity. And I said that earlier. When you have an infinity on the bottom, you're getting a 0. That's why this is a 0. If the bottom of a fraction is climbing to a big number, even if it's a big negative number, it doesn't matter, you're going towards 0. You're always flattening out, getting close to 0. Okay, so another couple ones to look at. Infinity plus 4, the 4 means nothing. It's still infinity. Log of infinity is infinity. Here, you're taking 3 from the right. So you have to kind of look at how this works here. As you plug in 3, just think of a number like 3.1, 3.01. What's happening is this number's getting very tiny in here. And if you think about how any log function looks, it's this one right here. As you get closer and closer to the 0 inside, your function is dropping, your log is dropping. That's what's happening here. When you plug in 3.1, the inside becomes 0.1. When you plug in 3.001, you get a 0.001 inside. You can't take a log of a 0 number, but you can take a log of very, very tiny numbers, becomes negative infinity. Okay, so now we talk about, if you don't remember this, you haven't seen it, indeterminate forms. Okay, so a couple of things before we get into these slides. Remember, if you get 0 over any number, it's 0. If you get any number over 0, it's infinity. If you get a number over infinity, it's a 0. If you get an infinity over a number, you get that. You get an infinity also. Okay, so those are just dealing with numbers. Now, if you have infinity over 0, realize what it's telling you. The 0 on the bottom means you're going to infinity. The infinity on top means it's going to infinity. They're basically agreeing you're doing the same thing. Just like right here, that's going to 0. Our trouble occurs when you get an indeterminate form like this, when you get a 0 over 0. So kind of stop and think what it means. When you have 0 on the top, that means your fraction is nothing. When you get a 0 on the bottom, well, that means your fraction is infinity. They're pulling away. They're giving conflicting information. That's why it's called an indeterminate form. You just can't see 0 over 0. You need more information about it. You need to know the behavior. And what it comes down to is, if you have a 0, remember, you don't actually have 0, but then the function is approaching 0 over 0. The question comes out to be is, who's approaching 0 faster. It's like who's going to win the race. It's either going to be if the top is winning, the answer is 0. If the bottom is winning, it's going to be infinity, or it's going to be some constant in between. We just don't know what it is yet, and that's what's going to happen. Other indeterminate forms, if you have an infinity over infinity, because again, remember, the top infinity means big, the bottom infinity means it's a fraction that's getting small. It's the same question: is it going to 0? Is it going to an infinity of some kind, or is it going to some constants? We don't know. We have an indeterminate form. Both of these are what are known as indeterminate forms. We need to figure out more information. Okay, now keep in mind, it doesn't matter if it's a positive or negative infinity or any combination of them, they're still considered indeterminate forms. Okay, so how do we deal with them? That's where this Hopital's rule comes in. So to just kind of keep in the back of your head, they only said 0, 0, but I'm sure they're going to say infinity over infinity in a bit. Just for our purposes, anytime you have 0 over 0, it's indeterminate. Anytime you have an infinity over another infinity, don't care if they're plus or minus, that's also indeterminate. Okay, and that's where we're going to do some things. So here's what we're going to do. We have to first always treat every problem like, well, let's see what we get. So let's plug things in. When you plug this in here, notice, and they factored it, you didn't have to do that. You could have just plugged in the 3 and, oh, let me go back. Not what I want to do yet. Now I know why we did that. Sorry, let's plug in the 3. 9 minus 9 over 3 minus 3, notice you get a 0 over 0. That's an indeterminate form. That's how they know it right there, just by literally plugging that stuff in. So the first step is, let's see if you can simplify this fraction a little bit. So how they simplified it is we factor. This won't always be the case, but when it does, let's see what happens. And you see how these things cancel off right here, and we're just left with this? Now, this function x plus 3 is not the same as that one exactly. They're almost the same, but there's going to be a slight difference. There's going to be a hole in this one on the left, no hole in the one on the right, but they're essentially the same function. And when you're looking for limits, the important part is the limits are going to be the same. So now that you have this one, now I can try plugging in the 3, and you notice that's how they get the 6. That's how you get your limit. Even though 6 does not exist, it's a hole, it's still the limit, and that's the answer to the question. What is that function doing as x approaches 3? Well, the y value is approaching 6. So that's your first way out of an indeterminate form, is you can do that. Now we get to something like this, and you're going to see it's not always going to be the same. First step, though, in every problem, plug in your numbers, your value of x. They tell you x is approaching 2. So let's plug those in, and you see I get a 0 on the top, I get a 0 on the bottom. There's my indeterminate form. Now, unlike the last example, we can't do any algebra. We can't do anything to clean this up. We can't make something cancel, so we're sort of stuck. No algebraic simplification process. This is where we're going to do our new rule. It's called Hopital's rule. Okay, now notice it can only be done when it's an indeterminate form. Okay, now that's whether it's 0, 0. They only said 0, 0, but it also applies when you have infinity over infinity. Just telling you that right now. So here's the process. It's literally going to be one of your simplest things you do here. Okay, your first step, like I said, though, is you have to make sure it's an indeterminate form. 0 over 0 or infinity over infinity. So here's the deal. Once you determine it has that indeterminate form, then you know Hopital's rule applies. And here's what Hopital's rule is. It's usually going to be because you have some sort of a fraction. That's why you're getting 0 over 0. So you take your original function, which is 1 over the other. You just take the derivative of the top and derivative of the bottom. Notice you're not doing the quotient rule. It's the way people would do the quotient rule wrong, where they do the derivative over the derivative. The quotient rule, remember, has a derivative of the bottom. The bottom times derivative of the top minus top derivative of the bottom over the bottom squared. That's not what we're doing here. We are just going to go and take the derivative of each, and we're going to get a new function, hopefully a simpler function, and then you kind of start over and say, well, now let's try plugging in the numbers, the number, whatever our limit is, like in this case, C. Plug that in and see what you get. Okay? So, show you what I'm talking about. Here's a problem. Again, when we plug in 2, we get a 0 over 0. So first step is we are indeterminate. Indeterminate form. That means you can do this L'Hopital's rule. So the way we do L'Hopital's rule, when they did this, we get a 0 on the top. We get a 0 on the bottom. So they check to make sure you get 0 over 0, or like I said, infinity over infinity. So the rule does apply, and here's what we do. We take the derivative of the top and the derivative of the bottom, and the top, just got to remember how to do these derivatives. E to the x derivative is e to the x. This one, you may not realize it, but it's e squared. It's a number. That whole thing is a constant. Remember, it's 2.7 squared. That's a number in your calculator. The derivative of a number is nothing. That's why it's gone. And then on here, the derivative of x minus 2 is just 1. So now our new problem is, what's the limit as x approaches 2 of e to the x? Well, the answer, now you basically start all over again. You plug in a 2, and we get e squared, and that is your exact limit. Okay? Now I want to cut out of here for a second and just show you some of this on Desmos so you can get an idea of how this thing looks. Okay, so here's our function right here. We have e to the x minus e to the 2 second. And that's going to be over x minus 2. Okay, so you see what's going on in this function. They're asking what's happening as x approaches. Okay, well, I guess Desmos didn't like the way this one looked here. Okay, well, my hope was to show you that this is our point that we were approaching. All right, there we go. That's the part I'm trying to see. I was trying to see that there's a hole right there. They just didn't really show it very well. But technically, at x equals 2, the graph doesn't exist. If you look at the domain, 2 doesn't work because 2 gives you 0 on the bottom. So it's undefined, but like I said, it'd be nice to see an actual little hole. That's how the graph's supposed to look. There's a little hole right here. And the question is not what's the value of it, is basically what is the graph approaching. But from the left, from the right, both cases they're approaching e squared. E squared is this 7.29, the number that you don't see right there. That's what they're approaching. So from the left, kind of look at what's happening with the y values. They're getting closer and closer to this number. And then from the right, look what happens to the y values. 7.39 or 7.37 or something like that is what it's approaching. That's what e squared is. That's what we're approaching. That's what we're trying to find here by L'Hopital's rule. So it's just kind of telling us that we can do that. So just to clarify, e squared is this 7.389. That's the number that we're approaching. So here's the 2. Kind of look at the y values. We're approaching 7.389. And then from the left, we're approaching 7.389. Okay, that's all I wanted to show you. Just give you an idea of what it is we're finding. We're still finding that value where the graph is approaching from both sides. Okay, so now that we have that, let's look at another one. So same thing, when you're doing these, it's, whether it says L'Hopital's rule or not, here's the thing I want to tell you. You're asked to find the limit. Don't assume it's L'Hopital's rule, because you're going to find L'Hopital's rule makes things really nice and easy. But your first step always is you need to check to see if the rule applies. And forget if even if you're looking for L'Hopital's rule, you just need to go and start finding this. The first step always for a limit is plug in 1. So I get natural log of 1, which is a 0. I get a 1 on the bottom. That's not a 0, which means L'Hopital's rule does not apply here. Remember, you're supposed to get 0 over 0. When I plug in a 1, natural log of 1 over 1, well, the natural log of 1 is 0, but 0, it's not 0 over 0, so don't do a derivative. Don't do L'Hopital's rule. We just clean this up, and guess what? That's just 0. That is my actual limit. We just do it like we normally would, just like you see here at the bottom. Okay, so not always is it, don't always assume every time it's going to be L'Hopital's rule. You have to plug in the numbers and assess the situation. Are you getting a 0 over 0? Are you getting an infinity over infinity? If so, then you can take the derivative of the top and the bottom. If not, then you got to go figure out what's going on. Okay, so you see here now, they showed an example. We know from the previous step the answer is 0. We got that. That function approaches 0 as x approaches 1. But let's say we did not look and follow rules and we just did L'Hopital's rule. We took the derivatives. Well, we get a 1 over x on top. We get a 1 on the bottom. That, when you plug in the 1, that becomes 1 over 1. You see we get a false limit. So be very careful. When it's not a 0 over 0, when it's not infinity over infinity, when it's not an indeterminate form, if you try L'Hopital's rule, you will get the problem wrong. So make sure you're aware that it only works when it qualifies. Okay, try another one here. Again, don't just do L'Hopital's rule. Let's plug in the 0 everywhere you see an x. So for the top, we get a 1, because notice it's e to the 0, which is 1, minus 1 minus 0, that gives me a 0 on top. Plug a 0 in here on the bottom, 0 squared is 0. So we have each of those, so we do get a 0 over 0, which means the rule does apply. We can do L'Hopital's rule. So we take the derivative of the top and the bottom. So the derivative of the top, remember, e to the 2x, it's e to the 2x, but because of the chain rule, we multiply by 2. The derivative of negative 1 is 0, so that's gone, and the derivative of negative 2x is negative 2. This is my new numerator. And on the bottom, of course, the derivative of x squared is 2x. So now we plug this in again, and so now we have a smaller limit. Hopefully, if you look at the original problem now, it's a better limit. But now you start over, and you still ask yourself the same question. How do I find this limit? Well, go replace every x with 0. And you notice when you do that, you get e to the 0, which is 1, so we get a 2 minus 2, which is 0, and a 2 times 0, so we get another indeterminate form. All right? So guess what happens? This means we can do L'Hopital's rule again. It still exists. You can do L'Hopital's rule as many times as long as you keep getting 0 over 0 or infinity over infinity. So now we get a 0 over 0. We already found out we got that. We got the rule, so we do the derivative one more time. So now I get a 4e to the 2x, and I get a 2. This time when I plug in a 0, I get a 4 over 2, I get a 2. Now I'm not getting an indeterminate form. I'm getting an actual number, a conclusion I can make. So the limit is 2. Okay, so that's what's happening on this one. Just takes doing a couple of derivatives and you get your answer. All right, so infinity, it's the same thing. You're going to plug in infinity in and see what happens. So remember what happens here. When you plug in infinity, it's e to the negative infinity. Just that one on top. E to the negative infinity is like 1 over e to the infinity, which is 1 over infinity. That's a 0. This little thing is a 0. This is a 0. And then we have the natural log of 1. Well, that's going to be a 0 also. You kind of see they break it down here. Pause this if you're not sure you need to see it. That's a 0. The bottom's a 0. Natural log of 1, you can even check it in your calculator. Any log of 1 is always going to be 0. So now L'Hopital's rule does apply. So we're going to take this original problem and we're going to do the derivatives. Again, this is the pattern the book will do. I don't like writing this step of derivative. I just want you to know, go find the derivative. Just go to this third line right here. So the derivative of this one, it's going to involve a couple things. First off, anytime you have a natural log, the derivative is 1 over the inside of it. That's why you have this 1 over e to the negative x here. Okay, so I'll kind of add some detail over here. The derivative is this. It's exactly as you see it, 1 over that. Then you have to multiply by the chain rule, which is the derivative of the inside. Remember that chain rule? So the derivative of 1 is nothing. The derivative of e to the negative x is e to the negative x. And then a chain rule again, which is multiply it by negative 1. That's how they got this thing right here. Negative e to the negative x all over 1 plus e to the negative x. And then, of course, the derivative of the bottom is just e to the negative x chain rule times 1. Remember, because the power is not just an x, it's a negative x, so you have to multiply by the derivative of that. So you have a negative e to the x on the bottom. And what we have to do next is it's going to involve a little bit of algebra. Remember, what this means is a couple ways you can write this here, but I'll show you one way. Let's say I leave it this for now. Remember, when you're dividing by something, it's the same as multiplying by the reciprocal of it. So that's a way I could take that denominator, which is a negative e to the negative x, and I can say it's the same as multiplying by 1 over negative e to the negative x, and all that to show that this and this cancel. That's why they have this 1 over 1 minus e to the x. This is all that's left right here. So now you plug in the infinity again. That whole thing becomes a 0. You get a 1 over 1, and you keep going until you get an actual number, or a 0, or an infinity. If you keep getting indeterminate forms, then you have to keep doing this process. But this is how you apply this L'Hopital's rule. So again, pause this if you need to see it. I'll move forward now. Okay, so, and notice that they're mentioning now if they're both infinities, it's going to work. That's why, I didn't want to start you over here. That's why I'm just telling you it's going to apply whether it's 0 over 0 or infinity over infinity. So in this case, now it can help you find horizontal asymptotes for functions if you know where L'Hopital's rule applies. So see what's going on here. What we're doing is we want to see what's the limit as x approaches negative infinity. Really what we're trying to see is on this function, as we go far to the left, what's happening to the y value? How do I draw this? Because what's going to happen is you're going to learn from their derivatives and all your local maxes and mins and inflection points and increase and decrease, and you're going to learn all what happens on the inside of a graph here. But the question is going to be, what happens to the graph over here? Does it go here? Does it go here? What happens? And they call this the end behavior of graphs. How do they finish? Well, we're going to do that first. We're going to know this left side by seeing what happens as we go toward negative infinity. What's the limit as x approaches negative infinity? As you go out to the right, that's going to tell us how to draw our function on the left side. So take every function, and what you're going to do is you're going to say, what's going to be the limit as I go toward infinity and the limit as you go toward negative infinity. So that's the question here. First off, so if you look at this, if you plug in negative infinity, now I'm not going to break it down like that. I'm just going to say this. What's the limit as x approaches negative infinity of this? Okay, so they plugged in the top and the bottom, and you see you get an infinity on the top, you get a 0 on the bottom. That's not an indeterminate form. Okay, what that becomes is you get infinity over 0, and I talked about that earlier. That means the same thing. That means you're going to get a really big number. So if you take this, I don't know if this is better to write it this way or not, but as x approaches negative infinity, both of these are getting very big toward infinities, and that's all we have to conclude is what are we going? Are we going to positive, negative infinity? Worst case, go plug in a really big negative number like negative 100, and you'll see you get 10,000 on the top, you get e to the negative 100. That's 10,000 times e to the 100. All I want you to see is this is a positive big number. So our conclusion is our graph is approaching positive infinity, as you see right here. All right? As x goes to negative infinity, the function's going to positive infinity. So that tells me if you're looking at your graph and you're trying to figure out where to draw this, just know, here's my graph. As I go out to the left, I'm going up. So this is how your graph looks, somewhere like that. It's going to start really high up here and come down. And that'll sort of be confirmed when you look at the increasing, decreasing, and all that. And we're going to do the same thing for the other side. What happens to your graph on the end behavior on the right? Let's look what happens as you approach positive infinity. Same thing, check the limit. If it's L'Hopital's rule, do it. If not, try plugging in a big number for x, and you'll see this is just going to also go to positive infinity. So that's how you go on the right. Okay? So now, you're looking at this function. You want to consider horizontal asymptotes. Well, look what happens as you approach infinity. You're going toward infinity. You're getting infinity on the top and the bottom. Okay? This means we have L'Hopital's rule. So when they say horizontal asymptotes, just so we're all clear here, here's a case. Let's just make a graph like that. Maybe like this. Okay, this is a case of, oh, here's a horizontal asymptote. As you go out, you start approaching that, but you never hit it, like sometimes with 0 or something else. So the question always is, well, what is that number we're approaching? I don't know. Well, you can if you go and check your limit as x approaches infinity, or whatever your function is. Let's go see what's the behavior of the graph as you go way out here. It's going to tell us what this number might be. So that's what they're doing. They're checking your graph as x approaches infinity, and they notice that you get infinity over infinity, which means you have L'Hopital's rule. So take the derivative of the top and the bottom, you get a 2x over e to the x. Well, I plug infinity again, and notice I'm still getting infinity over infinity. So do it again. Now you get 2 over e to the x, and the part they don't show here is when you plug in infinity, that's going to give you 2 over infinity. And remember, anything over infinity is going to be 0. That's how they know it's 0. So that tells me in my equation or my problem, if I have x approaching infinity or negative infinity, but infinity, and it's approaching a number, and 0 is just as good as the number 1, 2, 3, 5, whatever. If you're approaching a number, that is your horizontal asymptote. That's what's happening. Now you'll get more of a perspective as you do the picture, but what it's saying is your graph can do all kinds of stuff, but as it ends, it's approaching 0. Okay, that's the horizontal asymptote. Or maybe it's just doing this. We don't know if it's coming from the top or the bottom. That's where the other parts come into play. Remember our increasing, decreasing, local maxes and mins? That'll tell you. This just tells you how to end your picture on both sides. You take the limits as you approach both infinity and negative infinity, and that'll tell you what's going on. Okay, so now let's do some problems and see what exactly it is we're talking about here and how this stuff works, the practical applications. But again, just keep in mind, the whole idea is what's happening with these these graphs as you go far left and far right. That's really what it is when you're talking about a 0, something like that. So let's go back. Okay, so for your homework, I already have this pulled up. This is the homework for week 11, where we are right now. And you got a handful of problems. We'll just go through these one at a time. Let's look at number 3. Okay, try that again. Okay. So they want you, yes, this is the problem. That's it. They just want you to plug this in and make sure you understand what's happening. And a lot of this is pattern recognition, knowing what happens as your denominator gets bigger and bigger and bigger. Whole number or decimal, I think we just have to type in the 0.43. That's all there is to some of these. Like I said, you're going to get problems where they're going to have you plug in numbers, and they just want to make sure you understand what's going on as your numerator gets bigger or smaller and what it means to the answer. Okay, so even though the following limit can be found through algebraic simplification, they want us to use L'Hopital's rule. Now remember, even though you're instructed to use L'Hopital's rule, my thing to you always is, let's make sure it applies. So here's my problem. We have x plus 10 all over x squared. And I realize if you see this when you're on the homework, that 10 is not part of the problem. It's a limit as x approaches 10, and your problem is x squared on the bottom, x squared plus 18x plus 80. So remember the rule. Let's just plug in negative 10 and see what we get. That gives me 100 minus 180 plus 80. Looks like I get a 0 over 0, which means L'Hopital's rule is going to work. So we're going to do L'Hopital's rule. Sorry, it's supposed to say L'Hopital's rule. So the rule is your limit never changes. You're still approaching, x is approaching negative 10. We'll do the derivative of the top and the bottom. Well, the derivative of x plus 10 is 1. The derivative of the bottom is 2x plus 18. And now we plug in the negative 10 to get our answer. We get 1 over negative 20 plus 18. This looks like we get a negative 1/2. And there's our answer. Okay, clear that out. Pause that if you have any questions. And we'll look at number 11 now. Okay, so, all right. Again, even though they want you to try to use L'Hopital's rule, even though you might be able to algebraically simplify it, because the whole idea is later on, you will not have that luxury. You won't have the choice to factor. In fact, I'll make the argument it's even faster to just use L'Hopital's rule when it applies. So first thing is, let's plug in infinity. Now, when you look at this fraction, I'm going to write this fraction over here a little larger. When you start getting with polynomials and you start dealing with infinities, just remember this, all right? The highest power is all that matters. When I have 3x squared, when I plug in infinity, that's infinity squared, which is infinity, times 3 is infinity. All these other pieces are really of no substance. That's just going to be infinity. Here on the bottom, same thing. You're going to get a couple of infinities, which means L'Hopital's rule works. Okay, so the rule is we keep the limit the same. We're approaching infinity. And we take the derivative of the top and the bottom. That's a 6x plus 8, and that's an 8x minus 2. And then we plug in our infinities again, and notice I happen to get the same thing. I get another infinity over infinity. Well, then we do L'Hopital's rule one more time. That's a 6, that's an 8, and now there's no infinity to plug in. We just simplify this fraction, and 3/4 is our answer. That is our limit. Now, one of the things you can do, it's going to take a long time, but it's a possibility. Remember, as x approaches infinity, it's the same as you making a table and plug in big numbers like 100 and 1,000 and 1,000,000. And you see where's the y value trending, and it'll take a while, like I said, because this is a big complicated function with powers. But if you were to just play around with it and plug in 100 and 1,000 and 1,000,000 and take down the decimal you get, you'd be amazed that it's getting closer and closer to 0.75. In fact, that's the exact answer. That it's 75 is what you're getting. That's your exact answer of 3/4. Okay? This just saves you that headache of trying to plug this stuff in there. Because trust me, we'd be done with this problem before you even finish with the 100. Okay, but if you're ever stuck, this is the option right here, the old way to do things. Okay, let's look at number 15 now. Okay, again, L'Hopital's rule. Let's see what we get here. Don't assume you're always going to be given that instruction. I want you guys to be able to see when the rule and know why the rule applies, not just go L'Hopital's every time. Okay, so remember, as you plug in an infinity, you get an infinity on the top. On the bottom, you get infinity to the 10th, which is infinity. And I told you earlier, all logs to infinity are going to be infinity. So we can do L'Hopital's. It's just my shortcut, L'Hopital's rule. So we still have the limit as x approaches infinity. Now we take the derivative. Well, the derivative of x is 1. The derivative of natural log of x to the 10th. Well, remember how that works. It's 1 over x to the 10th. That's the rule for the derivative of a natural log. And then we got to multiply it by the chain rule, which is 10x to the 9th. Okay, and now I'm going to clean this up a little bit. Okay, so remember, when you're dividing by a fraction, it's like same as multiplying by the reciprocal. This is like x to the 10th over 10x to the 9th. Just take this little fraction and put it up top by taking the reciprocal. So 1 over x to the 10th is x to the 10th. And don't go to L'Hopital's rule. We're still trying to clean it up and see what we get here. Simplify whenever you can, and all of a sudden I get an x over 10. Remember the x to the 10th? 9 of them cancel with the x to the 9th. And now when you plug in infinity, you get infinity over 10. And that is just a plain infinity. So
your answer on this question should be the limit is infinity, and that's it. So let's look at number 19. Okay, so same kind of thing. They want us to plug it in as we're approaching, x is approaching 6. So my first step, so let me write this over here. We have the limit as x approaches 6 of the natural log of x minus 5 all over x minus 3. Okay, so first step, plug in the 6 and just see what happens when the smoke settles. Where are you? What do you have on the top and the bottom? Now, right now, I already see that I'm getting the number 3 on the bottom. I know no matter what else happens, there is no L'Hopital's rule. We should be able to get an answer here. Because remember, L'Hopital's rule is only when you get a 0 over 0 or an infinity over infinity. If you get any other regular number, you're going to be done with your problem pretty soon. You just have to make sure you answer the question. So the natural log of 1, remember, log of any log of 1 is going to be a 0. This answer is 0, and that is our answer. That's our limit right there. That's it. Some of these are that quick. That's all you have to do. If this was an indeterminate form, then yes, you'd be doing L'Hopital's rule and then plugging in and doing it again if you needed to be. But this case, and like a lot of them, don't assume L'Hopital's rule. Make sure you look at the problem carefully and always plug in to see, are we in fact getting a 0 over 0 or an infinity, to infinity over infinity. If we are, then we do L'Hopital's rule. If not, do something else. Okay, here, same kind of thing. We have the limit as x approaches 5 from the right side. Now, the right side, left side is not going to matter in terms of does L'Hopital's rule apply. It may come into play later if you're trying to determine if it's infinity or negative infinity. So keep that plus there. Don't just throw that away or ignore it. For now, I will ignore it because it doesn't make a difference. But it may have a huge bearing down the road. Now you're going to find that sometimes the hardest part of L'Hopital's rule is this step of the plugging in to see what you get. Okay, so I'm going to plug in the 5. It doesn't matter if it's 5 from the left, 5 from the right, or just a regular 5. You just plug in 5 and you see what you end up with. So we have 5 cubed, which is 125. Then we get 5 times 75. And notice I'm going to do this because you don't want to get these numbers wrong and make a mistake when you're doing this. You want to make sure you get everything exactly what it's supposed to be. So just at first glance, I can see the top is going to be 375 minus 375. That is going to be a 0. On the bottom, I have a 125 minus 15 times 25, which is again a 375, plus a 375 minus a 125, and that also gives me a 0 over 0, which means now I can do L'Hopital's rule. Okay, so look that over, make sure it's all because we had the 0 over 0. So hopefully this will make our problem a little more reasonable. We're going to find the limit as x approaches 5 from the right side and take the derivatives. So we get a 3x squared minus 75 all over a 3x squared minus 30x plus 75. And assume nothing. You have no idea if this is going to work or not. You just have to plug in the numbers and see what you get. So I get a 75 over 75. That's going to be a 0. On the bottom, I get a 75 minus a 150 plus a 75. Yep, I'm getting a 0 over 0. So we do L'Hopital's rule one more time. And it may be 5 more times. We don't know yet, but we just keep going through the process. Derivative of top and bottom, 6x, 6x minus 30. And now we plug in our 5 again. We get a 30. Right now I know no more L'Hopital's rule because I'm getting a number. On the bottom we get 30 minus 30. 30 over 0. And remember, whenever you get a 0 on the bottom, that's going to be an infinity. Now, the question is, which infinity is it going to be? Okay? Which one are we getting? So, we have to kind of look and see this. Let me write this over here. This is the function that we're left with. Okay? So, to determine which one, don't just end it. It's going to be an infinity because we have a 0 on the bottom, but we have to know which infinity it's going to be. So, what do? I'm going to plug in a number really close to 5. Let's just see what number it is. And this is where that 5 plus comes from. Let's plug in something like 5.1. And all I'm doing right now is I'm going to do the sign game. This gives me a 30.6. This gives me a 30.6 minus 30. That becomes 30.6 over 0.6. And you see what I'm looking for is that's a positive, that's a positive. We get a positive. So my confirmed answer is a positive infinity. Now, I'll admit, most students don't even look at that part, and they would have just put in infinity, and they would have gotten the answer right, but they would have gotten lucky. Sometimes this could have been a negative. If I had it coming from the left, it would have been a negative infinity because of the numbers you would have gotten. You have to play the sign game if you get a form that's going to be one of the infinities. Just notice it's not always clear cut. A 0 on the bottom, it definitely means one of these infinities, but you have to take it one step further and figure out which infinity it is we're talking about. Okay, let's look at number 27. All right, again, let's see what we have. Do not assume it's L'Hopital's rule. Go figure out what is happening here. X is approaching infinity. We have e to the negative x all over the natural log of 1 plus 5e to the negative x. Okay, plug in the infinity. We get e to the negative infinity. We get natural log of 1 plus 5e to the negative infinity. Okay, so let's talk about how this works here. Remember, this, and I'm going to run out of room, but I was going to write this. Remember, this is like e to the positive infinity on the bottom. That whole top is essentially a big 0. Okay, because that's 1, when it's a negative power, a negative infinity, it's getting a fraction, so you're going backwards and you're getting a 1 over some big number, you're getting a 0. Over here, it's the same thing where we have natural log of 1 plus 5 times 0, because e to the negative infinity is a 0. So that gives me natural log of 1, which is also a 0. So I know I have L'Hopital's rule. Okay, so L'Hopital. We keep our limit the same, x approaching infinity, and we take the derivative of the top and the bottom. Well, the derivative of the top is e to the negative x times the negative 1 because of the chain rule. On the bottom, however, we get 1 over that whole quantity, and then the chain rule says you multiply by the derivative of the inside, which is negative e to the negative x. So that is going to become negative e to the negative x on top, negative e to the negative x on the bottom, and then this little fraction right here flips upward to become that. And what I want you to see here is that these are all being multiplied together. These two things are exact, and they're just going to cancel off. So this now becomes the question that we're looking for. And we plug in our infinity once again, and we get 1 plus 5e to the negative infinity. That is our 0. So we're left with just the number 1. And that's our limit after all that. Okay, no more indeterminate form, no more Hopital's rule. There's, oh, what did I get wrong here? Look back. Okay, so that's what we had. Let me just clarify and find that mistake. Okay, there's one tiny bit I didn't catch. Here, see if anybody caught that. When we did this derivative, the derivative of the natural log, it's 1 over 1 plus 5e to the negative x. The chain rule is the derivative of this part right here that I talked about. It's actually negative 5e to the negative x. This is what I should have had right here. So I just forgot my negative 5. Major problem. So fixing that, let's go back over here. This should be a negative 5 also. So when I cancel, almost everything cancels. You'll see here the negative cancels with that negative. The e negative x cancels that one, but I'm still going to have a 5 on the bottom. That was the big difference. Okay, so not everything goes away, so let me just kind of pick up right here. Now when you plug in the infinity, you're going to get 1 plus 5e to the negative infinity over 5. This whole part right here is a 0, so that whole thing's a 0, and we're left with, now I think 1/5 should be our answer. Cross our fingers. And there it was. So one little chain rule mistake. You missed that, of course, you're going to miss the whole thing. So look at that over. See if that works. Let's go to the next one. Oh, looks like we're done with 4.3. Okay, so that should take you through, let's see, number 29 of your homework. If you kind of look at where we're at. Let's see. So, not loading yet, but back to homework number 11 here. We've done 4.3. Yeah, so that'll take us through basically the first 29. All right, so we're going to do, my next video will be on section 4 out of chapter 4, and that'll take you through the rest of these. So try these first half ones. If you have any questions, let me know. Don't forget your quiz from week 10 is due tonight as well. So get on that, and again, questions, let me know. Have a good one.